Today we're going to review three different forms of a quadratic function that we looked at this year and what you can glean from looking at them in that form. What information does the equation tell us about the shape of the graph, where the vertex is, where the x-intercepts are, things like that. So our first form that we encountered was standard form. And here's an example, or here's generic standard form right here. And when a quadratic is in standard form, if we memorize this little equation, negative b over 2a for x, that is called the line of symmetry. But I just pretty much think of it as this is going to be the x-coordinate of your vertex, which is really useful to know if you're going to graph it. So here's an example. In this example, a is 1 and b is negative 4. So when we find the line of symmetry, it's going to be negative 4 over 2 times 1, which is 4 over 2, which is 2. So we know the vertex of this graph, the x-coordinate of the vertex is at 2. So in order to find the vertex, what we do is we plug 2 into our equation. So that's going to be y equals 2 squared minus 4 times 2 minus 6. So that's 4 minus 8 minus 6. Whoops. 6. Which is 4 minus 8, negative 4, minus 6 is negative 10. So if we graph this quadratic, we should see that its vertex is at 2, negative 10. So here's a graph of that function, and sure enough, we have the vertex at 2, negative 10. So that's really the finding the vertex using negative b over 2a with the standard form. But you should also know, and most of you do from my experience, that the a value here determines the shape of the graph. So if a equals 1, we can expect it to be facing upward and for it to be the same shape as y equals x squared, which would be the parent function. So in other words, if you think of this vertex as the new origin, if you will, look at the pattern of this quadratic. When you go out 1, you go up 1 to get to the next point. When you go out 2, 1, 2, 3, 4, out 1, up 1, out 2, up 4, that's the same shape as y equals x squared. So if you know how to find the vertex, negative b over 2a, to get your x value, plug that in, get the y value, you'll have your vertex point, and then if the a is 1, you'll know what the general shape is. Okay, the next form, we don't really talk about this so much as a form. Like you hardly ever see this in its like a formula, but we've encountered it many times in functions. So let's take an example. I'll just make one up here. Let's say this is negative 2 times x plus 2 times x minus 6. Okay, so when we encounter a quadratic function that's been factored like this, the number out in front here, if there is one, determines the shape of the graph. So just like in every other form of the quadratic, that determines the shape of the graph. So the shape for this is going to be upside down because it's negative. The fact that a is 2 instead of 1 is going to be skinnier than we're used to seeing. Okay? So that's the general shape. And then what else does this tell us? It doesn't tell us the vertex just by looking at it, but it does tell us the x-intercepts. In fact, sometimes this is called intercept form in some textbooks. Okay, so if we solved this using the zero product property, so that means setting it to 0 and figuring out what x is, x would have to be -2 and +6. So what that tells us now, we have an x-intercept at -2 and +6. If we wanted to find the vertex is, the line of symmetry for it is going to be halfway between -2 and 6. So if we take the average of those two, we add them up, divide by 2, that's going to be 2. So the vertex will be 2 something. Now to find that something, we need to plug it into our equation. So x plus 2 would be 4. 2 minus 6 is -4. So that's 4 times -4 is -16 times a -2 is going to be 32. So that vertex is going to be way in the hay up there, like way up there. And it'll be a skinny graph like that. So I'm going to use Desmos to graph that on the next slide so we can double check, okay? So again, this is when you have a quadratic that's all factored out. Okay, we can easily determine what the x-intercepts are, and we can get the gist of the shape looking at the number out in front. If there is no number out in front, that means a is 1, and it'll have the same shape as the previous slide. Just your basic y equals x squared shape. So here's a graph of this function, and we can tell that it does have x-intercepts at -2 and +6, and the vertex is at 2, 32, just like we predicted from the information we gleaned by looking at the function and doing a little bit of calculation. Okay, and the third form of a quadratic that we're looking at is what I call vertex form, and I think your textbook called it graphing form. And this, if you go back to the first, some of the first lessons of this new quarter that when I started posting work, we were working on this, I think, yeah. So anyway, this is a really handy dandy form because your HK tells you what the vertex is. No calculation necessary. The vertex is HK. The A is still out in front, and again, that determines the shape of the graph. So if A is 1, it's your standard y equals x squared shape. If A is negative, it's upside down. If A is large, it's skinny. If A is a fraction between 0 and 1, it's wider than normal. So let's look at some examples, and then we'll graph them on the next page. Or let's just practice finding the vertex first of all. So let's take a look at, let's say we have this function here. The vertex would be 3, -7. If we have this function here, the vertex is -1, 10. Notice it's kind of counterintuitive right here. That's because, see how the formula is x minus h? So when you have x minus 3, h is 3. when you have x plus 1, it's like having x minus -1. And that's what the formula is, x minus h. So when we put this into the formula, x minus -1 is the x-coordinate of the vertex. I just kind of memorized that fact that it's for the x-coordinate, it's going to be opposite of what it looks like it should be. So if I see a -3 in there, I'm like, oh, it's +3. So basically this shifts the parent graph. The parent graph would be the same shape as y equals 2x squared. And that graph would be shifted right 3, down 7 for the first one. I'm just talking about this one. So here's an example of quadratic function in vertex form. And we see the vertex will be 3, 5. And the shape of the graph will be skinny and going upwards. So we call that vertically stretched by a factor of 3. And that's what we have here. 1, 2, 3, 5 is the vertex. And it's on the skinny side. Okay, in our last example, here's the function in red that's graphed. We see that the vertex will be -8, -6, and that's where this is the vertex for the red graph here. The a is 0.5, which makes it wider than normally, wider than yx squared, and I put the other two here for comparison. So in the green, you see a graph that's 0.5x squared. So it has the same a value as this one, and you can see it's the same shape. It looks a little bit different because the red one is shifted down, so you see a wider part of the graph, but if you were to move this one on top of that one, it'd be the same shape exactly because their a's are the same. Now we compare those two to what we have here. Y equals x squared is like your basic quadratic parent graph, and that's in purple here on the graph. And you can see the 0.5 makes the parabola wider than that. So when a is a number between 0 and 1, it's going to widen the parabola.